So hey everyone, welcome to my presentation about BDJB. My name is Nguyen, also known as The Flow in social media, and today I'm going to talk about the very first Blu-ray Disc Java Sandbox escape. Different from other talks at this conference, mine will be about higher level vulnerabilities. The content is the following. First, I will give an introduction about myself and the motivation behind this work. Then, I will briefly cover the Java security model, and I will present vulnerabilities that I've discovered, which allowed me to escape the sandbox. Next, I will explain how I got native code execution and how I even managed to get arbitrary code execution. And finally, there will be a recap and even a live demo. Alright, about myself. I'm an information security engineer at Google, doing cloud vulnerability research. We focus on low-level security. We actually have open headcount in our team, so if you are interested, feel free to reach out after the talk. I'm also a PlayStation hacker and have been in the scene for over 10 years. For the PS Vita, I have released multiple jailbreaks, which allow people to run homebrews on their devices. And the latest work is the GTA San Andreas port, where I managed to load the Android binary on the PS Vita and made the game fully playable. For the PS4, I have mainly focused on FreeBSD kernel exploitation, and for example, the last 3 jailbreaks are abusing kernel bugs found by me. What was the motivation behind this work? Of course, as a PlayStation hacker, I wanted to hack the PS5. All public user land exploits so far were using WebKit as the entry point. However, the PS5's AMD CPU now supports execute-only memory, and it is enabled for the text segments of all modules. This mitigation makes a WebKit exploit much more difficult to pull off. The main reason is that JIT is not enabled in the render process, so we need a ROP chain in order to get native code execution. However, since we are blind, we cannot read any executable pages and hence cannot identify ROP gadgets. The other reason is that the WebKit sandbox has improved lately. For example, access to dev files has been restricted, and apparently some syscalls like IO control are now blocked. However, the main motivation was to explore different attack vectors on the PS4. I wanted to work on a novel technique, one involving physical access using a USB device or a disk. And for these, exploiting the file system is a possibility. As their implementations are in the kernel, a successful attack there immediately grants you kernel privileges. However, that is quite difficult, especially blindly, because we somehow need to determine addresses, make calculations, and in particular, to bypass ASLR. For that, having scripting capabilities would be of desire. It turns out that Blu-ray discs can run Java code, which is a very interesting attack surface. What is Blu-ray Disc Java, or in short BDJ? It is supported on the PS3 to PS5, on the Xbox One, Xbox Series X, and other Blu-ray players. It is used for advanced content, such as games, menus, and interactive videos. And there are tools publicly available for compiling and signing such jar files. Where the signed jar files simply have a bit more permissions, and for example can access the persistent storage or the network. More details can be found at blueplay.com. What is the attack surface of BDJ? We have 3 main attack vectors. We have the JVM, which parses and executes the Java bytecode. We have GNI functions, which are native methods, and we have Java classes. For JVM, we can search for OpenJDK CVEs and look out for type confusions, memory corruption bugs. However, there are not many proof of concepts available for these. For GNI functions, we can search for memory corruption bugs in the C++ implementations. Namely, the BDJ stack has a lot of native functions. However, that requires a lot of reverse engineering. And finally, for Java classes, we can search for Java privilege escalation bugs. While it's only a small attack surface, it is obvious what to look for. And that is the attack vector that I focused on for 2 months and found multiple vulnerabilities for. As a setup for this research, I ordered a BD burner and some BDRE disks. Note that BDR disks are only writable once, so especially since you cannot load classes remotely, you have to burn the disk again and again for every single test. Now, let me briefly introduce you to the core concepts of the Java security model. For that, I will paraphrase a few sentences from the Java documentation. The Java security model is based on controlling the operations that a class can perform when it is loaded into a running environment. For this reason, this model is called code-centric or code-based. A security model policy defines the protection domains of an environment. And a protection domain associates permissions with code source. The TLDR is every class file is associated with certain permissions. For example, Bootstrap classes have full permissions, while untrusted classes like ours on the Blu-ray disc have a few only. An important component of the Java Sandbox is the access controller, which is used for access control operations and decisions. There are two main functions. First, check permission, which checks that the intersection of all permissions of each protection domain on the call stack implies the requested permission. Then there is doPrivileged, which is used to run a method in privileged context. How it works is, it marks the caller as privileged in order to ignore permission checks before the caller. And finally, there's the security manager, which is a class that allows an application to implement a security policy. It also contains a check permission method, which essentially calls the access controller check permission underneath. To show you an example of a security check, consider the following code. GetProperty from the system class gets a property based on a key. However, before doing so, it checks whether the user has the necessary permission. If a code source without the necessary permission calls this method, then a security exception will be thrown. If a trusted class wants to call this method, but untrusted functions are on the call stack, then the intersection of all the permissions will be empty. So in order to avoid this, the trusted method needs to use doPrivileged in order to ignore earlier functions on the call stack, so that the permission check can always pass, for example, to get the property of the package access. Now that we know a bit about the security model, let's see how we can break it. When the Java application is executed from the Blu-ray disc, JVM is launched with the following flag. These are Bootstrap classes which are fully trusted and hence have full permissions. For example, bdjstack.jar contains many interesting classes. As mentioned earlier, finding privileged escalation bugs is straightforward. You basically search for doPrivileged calls and see if malicious stuff can be done. For example, creating objects or invoking methods in privileged context. The first vulnerability is in the user preference manager, where they call doPrivileged. And underneath, a file is read from hard disk and deserialized. You're probably familiar with Java deserialization bugs. They often allow remote code execution, but they may also allow privilege escalation. Let's see how. The user prefs file is located in a folder in which the user has write access to, and hence, the file can be overwritten with a malicious serialized file. And during deserialization, the accessible default constructor is called for the first class in the inheritance hierarchy that does not implement serializable. And since the invocation is in privileged context, permission checks in the constructor can thus be bypassed. What class would be interesting to instantiate? The class loader is an interesting target. We create a subclass which extends the class loader and implements serializable. As mentioned before, the first constructor whose class does not implement serializable is called. And since the payload class loader implements serializable, its constructor is not called, but the constructor of the superclass, which is the class loader. And hence, our payload class loader will not be on the call stack, and permission checks in the class loader constructor will pass. When read object is called, we then assign the instance to a public static variable. And once we have that instance, we can call new payload on it. The interesting part is we can now call the protected method define class to load the payload class with an arbitrary protection domain. In our case, one with full permissions. Unfortunately, this has been mitigated upstream, and exploiting Java deserialization for privilege escalation is no longer possible. The second vulnerability is in the IXC proxy, where a method of an object can be invoked based on its name and signature. It calls doPrivileged, where underneath it locates and invokes a method. What kind of methods can be located? It can only locate methods which are public and non-static, whose classes implement an interface, and where the interface's methods throw remote exception. On the right-hand side, you can find such an example. We have my interface, which declares my method, and we have my implementation, which implements the my method of my interface. How is this useful though? If we just call an untrusted method in the doPrivileged block, then we won't be able to gain any additional privileges. What we need to do is to call a trusted method with it. Consider a target method which is public and non-static, and where the target's methods class is inheritable and instantiatable. For example, consider the target method in target class. We can invoke this method in privileged context as follows. We create an attacker interface which declares the same target method, however, which throws remote exception in addition. And we create an attacker class which extends the target class and implements the attacker interface. What is important here is that the attacker class does not override the target method. Namely, target method is inherited from the target class. When locating and invoking this method, the untrusted attacker class will not be on the call stack, meaning that everything within the doPrivileged block will come from trusted code only. For a real example, consider the file class as a target. Permission checks are in the file constructor, permission checks are not in the file constructor, but for example in the list method. We create a file interface which declares list, and we create a file implementation which extends the file class and implements the file interface. With our primitive, we can now call list with all permissions, and therefore we are able to list arbitrary paths and can use that to dump the application directory and obtain jar files on the PS5. With the ability to call methods in privileged context, we can invoke a few interesting methods, but there are certain limitations, as described earlier. And with the following gadget, which is only available on the PS4, we can instantiate a class with one argument, and chaining that with the privileged method invocation, we can now also invoke constructors in privileged context. The BDJ stack contains its own security policy implementation. In the getPermissions method, there's an interesting condition. If the location of the code source begins with a certain prefix, all permissions are granted. And that is the number one mistake when handling and checking file paths. If path traversal is possible, then this condition can be triggered to gain all permissions. And that's what we do. Plugging all together, with our privileged constructor invocation, we instantiate a URL class loader with a malicious path. We namely point it to our jar file, but with a prefix that fools the security policy. The path traversal is per se not a vulnerability, because creating new class loader instances is not permitted in the first place. This method only works on the PS4 because the service class mentioned earlier is available there only. How to escape the sandbox on the PS5 with this vulnerability will not be disclosed and is left as an exercise. What shall we do with all the permissions? The payload class has one purpose only, which is to disable the security manager. With the security manager disabled, we can namely access all internal classes. The most interesting class to access is the sun misc unsafe, which we can get an instance from using reflection. What this class allows you to do, you will learn next. Namely, once you get access to the unsafe class, you get native code execution. And for that, we want to have three primitives. From Java, we want to access native memory, we want to find native methods, and we also want to call these native functions. For native memory access, we get it for free, because that is what the sun misc unsafe class is for. They are namely native methods like getLong, putLong, allocate memory, and free memory, which allow you to read, write, allocate, and free native memory. Using that, we can also construct an address_of primitive to return the native pointer of any object. We do so by putting the object's pointer into the value field of the long object, and then we can simply retrieve that pointer. As mentioned at the beginning, the PS5's AMD CPU supports execute-only memory and enables it for all the text segments in both kernel and user land. With this mitigation, we are not able to read executable pages and, for example, identify functions based on opcodes. We can read the data segment, though, which is useful to infer addresses of certain functions, but that is quite cumbersome and only works for a few functions. It turns out that the class loader native library contains a find entry function, which calls DLSim underneath, and that is the perfect gadget which we can use to identify addresses of all exported functions from Java. It is also firmware agnostic, as we only need to provide symbol names. The last primitive we need is a way to invoke these functions from Java code. In particular, we want to invoke them with arbitrary arguments, and we also want to get the return value from it. For this purpose, there exists an interesting function called setContext, where the function is from libunwind. It is similar to longjump, but it also restores all the argument registers, which is a perfect gadget for function invocation. However, to make that work, we also need to get other registers, such as RBP or RSP, so that we can restore them safely. For that, we can use setJump, which works under the assumption that the registers remain the same between the setJump and the setContext calls. How can we trigger that gadget? For that, we need a RIP control. We need to find an interesting object which we can fake or corrupt, whose class contains a virtual table, that is, virtual function pointers, and where the return value is sent back to the Java code. We don't need to control any arguments, except the buffer of the first argument, which is essentially this object. The array class contains an interesting virtual function. It is called by the native function multi-newArray, and where the object comes from the first argument, the component type. The interesting property is that the return value is the object that is returned by the multi-newArray. In other words, the return value is sent back to the Java code as we desire. We declare a native method in our API class and resolve it to the native function using our DLSim primitive. We do so because we want to have different types. Instead of returning an object, we want to return a long. And instead of using a class as the first argument, we also want to use a long. Then we call it with our fake object as component type. This fake object we can simply allocate on the heap. And after some dereferences, multi-allocate will be called with the fake array class object as the first argument. As the function pointer of multi-allocate, we first use setJump to save all the registers, and then we use setContext to restore them and to provide our desired arguments and function pointers. And we basically have achieved ROP-less code execution. there was one problem on the PS4. After a lot of function calls, it would just crash. For some reason, the stack pointer might be different between the two multi-allocate calls. Remember, the first call is to set jump and the second to set object. It turned out that JIT optimization would kick in after a few function calls. And the solution for that was easy. I used a for loop for the two function calls, and then I trained the Java function by calling it more than 10,000 times with one iteration only. And that trick was enough to trigger the JIT optimization at an earlier stage. And that way, the stack pointer would remain the same afterwards. After all the hard work, we finally have a native API with all the desired primitives. We can allocate, free, and access native memory. We can find native functions, and we can also invoke them with arbitrary arguments. The exciting thing is, it can even be used in Java threads, which means that we can do native function calls in parallel, which is useful, for example, to exploit race condition vulnerabilities in the kernel. With the ability to get native code execution, we can call some native functions, but we cannot yet execute arbitrary code. We can't simply call mmap, for example, because JIT capabilities are granted to certain processes only. In particular, no process is allowed to call mmap with write executable permissions. Instead, one needs to set up a shared page, which is mapped as read executable in one process and read writable in another process. That's what Sony did with the PS4. They moved all the JIT functionalities of the JVM runtime to a different process and communicate with it using Unix domain sockets. On the PS5, JVM JIT is unfortunately not supported. To show the concept visually, consider the runtime process, which maps the JIT page as read executable, and the compiler process, which maps the JIT page as read writable. Via Unix domain sockets, the runtime process can now request the compiler process to do JIT optimization, which is to write to the JIT page. If we manage to exploit the compiler process, then we can write arbitrary payloads into the JIT page, which the runtime process can then just execute. The third vulnerability is in the protocol between the two processes. Namely, the runtime process can provide an untrusted pointer in the structure, and the compiler process will simply make a backup of the request at that location. In other words, we have a write what where primitive. Exploiting the bug is quite easy. We don't really need to get code execution in the compiler process. We can simply use the primitive to write our payload. And that works because the JIT page has the same address in both the runtime process and the compiler process. So we let the compiler process write the payload, and then we can simply execute it in the runtime process. And that allows us to write C code as the next stage of the exploit chain. As said before, the PS5 does not support JVM JIT. Otherwise, that would have been useful to run homebrews already. But on the PS4, this capability is quite practical for kernel exploitation because there's no supervisor mode execution prevention. So one can simply get rip control in the kernel and return to the C payload. That was the whole exploit chain. So to recap, to get from Sandbox Java code execution to arbitrary code execution, we first need to escalate privileges, and we do so by looking for do privileged calls where we can trick bootstrap classes into loading our payload class with full permissions. Then we can install our native API, which should have 3 primitives. Before that, we need to disable the security manager by setting it to null. And then we install the native API, which should have the 3 primitives. We should access native memory, which we can achieve using the sun misc unsafe class. We want to find native functions, which we can find using the find entry from the native library. And finally, we want to call these native functions, which we can do using setJump and setContext via the multi-allocate. And finally, in order to execute arbitrary code, we just send malicious requests to the compiler process to write our payload. And the end result is we have userland code execution using the Blu-ray disc, which is 100% reliable because it does not rely on race conditions, on heap spraying, or other techniques. It is also firmware agnostic because it only relies on a few structure offsets. And with a single disk, we can hack any firmware. The exploit works on the PS4 up below firmware 9.5 and on the PS5 below firmware 5. Very likely, the PS3 is exploitable as well because they all share the same BDJ stack. And I used that entry point to chain with a kernel exploit and was able to enable the debug settings on the PS5. All right, now there will be a live demo. So take a look on this monitor here, which is quite small. I hope you can see something. And then we insert our Blu-ray disc, which even has a unique icon, and we can simply launch it. And now we got a notification on the system, and we would exploit the kernel in 10 seconds. So the whole part here is 100% reliable, as mentioned before. The kernel exploit might not be as reliable. Let's hope it will work. Or maybe we'll just panic. Yeah, likely it's just panicking. Let's try it again. See the notification again. We also say hacked planet at hardwear.io. Yes. So we were able to win the race. So as a spoiler, that's a race condition vulnerability that we exploited. And we were able to get read-write primitives in the kernel. And there are some nice kernel pointers. That's it. That's the BDJ exploit. Yeah. Thanks, Sony, for approving this talk and for resolving the vulnerabilities and for their HackerOne bug bounty. And thank you for your attention.
Do we have questions? Hello. So first, awesome talk. Thank you very much. So at least two questions. So I didn't know about anything about Java privilege escalation bugs like this, especially based on Java classes. So this is fun, I guess. So did you look into the bootstrap classes of JDKs itself? So in your class path, the first bootstrap classes for things like that, for, I don't know, Oracle Hotspot or JDK or something?
That's a good question. So there exists the runtime Java file, but it is super new, like from 2019 or so. So I didn't expect to find any 0 days in the JDK itself. But as I said, there exists the bdjstack.jar, which contains a lot of jar files, and they all have full permissions. So I was mainly looking there.
Yeah, makes sense. Okay. So may I ask something? Because maybe I just didn't understand it. Highly probable. You used a reflection gadget to get to the native world, so to say.
Mm-hmm.
So I was just not sure. I know that you can load native libraries with JNI. But is the SunMISC unsafe namespace, is this already JNI, or could you use JNI to load a shared native library as well for your exploit chain?
That's a good question.
Because I was not sure if the namespace is the same. So actually, if it is JNI, or you could maybe...
So there's the unsafe implementation in the JNI, yes. That also lives in the JDK.
Yeah.
Whether you are able to load other libraries, I'm not sure. Maybe.
Yeah, I'm pretty sure.
For the PS4, you would need. You are only allowed to load signed modules anyway. So I didn't look into this method.
Okay, all right. Thank you.